In this video, we're going to talk about a second factor which is important for evaluating resonance forms. We're going to see that it involves the octet rule and making sure that we follow the octet rule. So let's draw out two different resonance forms of, let's say, this protonated ketone. So in the last video, we were talking about how we like to minimize charges if possible. And in this case, we actually can't not. So we still are going to have a charge of +1 no matter what in this molecule. So I'm just drawing this out. We have two choices here between this molecule on the left as a resonance contributor and the molecule on the right. And the question is, which of these two do you think is going to be more stable? Which of these is going to make more of a contribution to the resonance hybrid? Okay, so look at this molecule on the left and molecule on the right. So like I said, last time we were trying to minimize charges, but notice this has a charge of +1 and this also has a charge of +1. So there's no difference in charges and there's one atom with a formal charge of +1 and another atom with a formal charge of +1. No difference there. So given this, how can we evaluate the stability of these two different resonance forms? Well, here's one thing to note. If you count the number of electrons around the oxygen here, you'll note that there's a bond to hydrogen, there's 2 bonds to carbon, and there's a lone pair. So there's a total of 8 electrons, so 8e. And also around the carbon, it's got 1, 2, 3, 4 bonds, so it's also got 8 electrons. And if we look on the molecule on the right, the resonance form on the right, 1, 2, 3, 4, and then 2 bonds, this also gives us 8 electrons. However, if you look at the carbon on the bottom, this is a carbocation. This is a carbocation. So it actually only has 3 bonds and it doesn't have any electrons around it, so it bears a charge of +1. There's only 6 electrons around this carbon. So this does not, there's no full octet. Okay, and because it lacks a full octet, this is actually going to be a minor contributor to our resonance hybrid, and this is going to be a major contributor because every atom here follows the octet rule. And you might think, oh, isn't it strange we're putting a positive charge on our oxygen here? But if you look or think about where the electronegativity lies, actually, oxygen, remember, oxygen's got a high electronegativity. It's actually going to still be the partial charge on oxygen still going to be actually partially minus and or delta minus, and because it's more electronegative than hydrogen, it's more electronegative than carbon, so it actually bears this charge of it's slightly electron rich, even though it has a formal charge of +1, and that's why sometimes I say that formal charge can lie. Now there's actually a third resonance form which I didn't draw here, but we can draw this as well and show why this is even worse. So we could also draw this resonance form where we'd have a lone pair on the carbon, and notice that we've got 8 electrons on the carbon. However, in this case, we've got 6 electrons on the oxygen, and it lacks a full octet, no full octet. This is basically essentially does not contribute to our resonance hybrid. Why not? Why might it not contribute? So it's basically insignificant. Well, because oxygen is more electronegative than carbon, right? So oxygen, like we say, sometimes is sort of greedier for electrons than carbon is. It pulls electrons towards it more than carbon. So it doesn't make sense to draw a resonance contributor where carbon would have this pair of electrons rather than oxygen. So this is why this is not a significant resonance hybrid. Not only the fact that it lacks a full octet, but if you're going to have an atom that lacking a full octet, don't make it oxygen or nitrogen. Make it carbon. Okay, so bottom line here is make sure that everything has a full octet. So let's draw one other example here, and maybe we'll show a different type of structure So we have CH2 plus, and let's say CNH2 with a lone pair, and CH3. Okay, and let's draw, hydrogen. And let's draw a resonance form for this that looks like this. CH3, NH2, positive charge on the nitrogen, and carbon, CH2, hydrogen. Okay, and if you're following the arrows, we could get there by taking a lone pair from the nitrogen and then forming the nitrogen-carbon pi bond, and then taking the pi bond, pair of electrons from the carbon-carbon pi bond, and moving that pair of electrons to this carbon-carbon double bond here. Okay, now which of these two would be more stable, the one on the left or the one on the right? Well, again, if we look at the number of electrons around everything here, we have 8 electrons around the nitrogen, so we've got a lone pair and 3 bonds, that's 2 to hydrogen and 1 to carbon, and everything else here has 8. This has 6. There's 6 electrons. So that lacks a full octet. Now, what about this one on the right? Well, this one on the right, we've got a nitrogen with 2 bonds to hydrogen, we've got 2 bonds to carbon, so this has 8 electrons. So same as before, except now it bears a formal charge of +1. And now the CH2 here also has 8 electrons around it. So it actually has a full octet. So this now has full octet, so this should be our major contributor, and this over here should be our minor. So our resonance hybrid would have more of the structure on the right than it would have the structure on the left. So, the bottom line here is really that we want to have full octets. Full octets are preferred over forms lacking a full octet. Okay, so just keep that in mind when you're evaluating resonance forms. If you see one of the resonance contributors that has every atom having a full octet versus one which one atom lacks a full octet, the one with all atoms having full octets is going to be more stable. Next one, we'll talk about how to stabilize negative charge.